Hello viewers. Now this is a question from A-level physics and the chapter is thermal physics. I must tell you that this part had two marks, and if you write this, your two marks are confirmed. In part B, an electric heater is immersed in some melting ice. This is the electric heater and this is melting ice. That is contained in a funnel. This is the funnel, this one, as shown in figure. I have drawn the figure for you on this paper to make it easy. The heater is switched on, and when the ice is melting, for example, the water is dripping from here into the can or container, the mass m of ice melted in 5 minutes. Mass m melted in 5 minutes, this is the column of the table, is noted. Together with the power P of the heater, power P of the heater, power in watts, time in minutes over here, please keep it in mind. Together with the power P of the heater, the power P of the heater is then increased. Can you see the power was 70 watt for first 5 minutes and 110 watts for second 5 minutes. A new reading for the mass m of the melted ice in 5 minutes is recorded. For 70 watt power, the mass is in grams is 78. I can write down unit as grams. And for 110 watt power in 5 minutes, 114 gram is obtained in the container, as this ice is a cold body and atmosphere or surrounding is a hot body, and even if the heater is not switched on, ice is going to absorb heat from surrounding and then keep on melting. So we have to keep in mind that ice is gaining heat from atmosphere, and when the heater is switched on, it will also gain heat from the heater. So we have to keep in mind that this heat gained from the atmosphere and consider this and put it in our value, otherwise our answer is going to be wrong. Secondly, you have to keep in mind that the heater, when switched on, will start melting ice at a rate which increases by time, but there will be a time when the rate of melting of ice because of the heater is going to become constant. You have to be very observant, and when the rate of melting ice becomes constant, then you have to start taking the time for 5 minutes. So stopwatch has to be controlled in a very, very professional manner. Now, using data from table 3.2, we get two equations, one with the power 70 and mass per gram 0.26, the other 110 and the mass per gram 0.38. And when we subtract equation 2 from equation 1, this is the magic of mathematics, that we are eliminating one quantity from simultaneous equations. So we get minus 40 is equal to minus 0.12 L. So L is equal to 40 over 0.12, which is 4000 over 12, comes to be 333.33, and rounded off to 2 or 3 significant figure, 330 joule per gram, because we have 3 or 2 significant figures. Right. So if we have written this in this answer in the space given, that is actually joule per gram. So I'm going to write down that answer here. L is equal to 330 joule per gram. This is the answer required, and we scored 3 out of 3 marks. But if it was joule per kg, then we would multiply this with 1000 and write down this. This is just an additional information here. This too. And it is asked the rate h of thermal energy regained by the ice from the surrounding, using equation 1 from part 1 above. So 70 plus h is equal to 0.26 into L. Put in the value, solve, and get 17 joule per second or 17 watt, because he is asking you the thermal energy gained by the ice for the surrounding. So thermal energy is 17 joule and power is 17 watt, and get 2 marks. So we come to the end of this question. I have tried to explain the question in detail. If it has helped you, kindly like my video and subscribe for my channel. Thank you.